Now here's the second video that you're watching. You just finished sections 5 and 6 out of chapter 1. Now we're going to skip over 7 to 9. Those will come later. We're going to do 10 and 11. They're very short, which is the reason I've chosen to do that. 7, 8, and 9, on the other hand, are really going to require quite a bit of concentration on our part. So let's get started. Axioms and properties. Well, we know quite a few properties already, don't we? Properties of numbers. We've looked at those. And axioms. What in the world does that mean? There's a lot of vocabulary for us to learn. Column proofs. You remember back to geometry, you did proofs there. We're going to do some proofs here. Also in geometry, remember talking about postulates? You had theorems, which had to be proved. Statements which required proof were called theorems. And then you had other statements which were considered so obvious, we'd accept them without any proof. Without proof. Today we're going to be talking about axioms like postulates. These are properties which are so obvious that we'll accept them without any proof. We've already worked with 5 of the 6 axioms that we have that we're going to discuss in this section. We called them properties, and we didn't bother proving them, did we? Commutative, that was for addition and multiplication. Associative, that was for addition and multiplication. Distributive, that was you could multiply something over a sum. Identity elements, for addition, that's 0, and for multiplication, it is 1. We talked about inverses for addition. The inverse is a change of sign. For multiplication, the inverse is the reciprocal of what your multiplier is. The new one that we're going to add, so that's 5. The new one, the 6th one, is right here. It's called closure. We're going to be speaking about sets. Here's a little, I've added closure in at the top. In addition, what closure is, if we look at the set, when you see these curly brackets, you want to think of the word set. When we look at the set of all real numbers, if we add any two all real numbers, we will get a unique number. Closure, here's a definition down here. Maybe we should jump down here and take a look at that. The offspring of any two members combined by the operation, and in this one we were looking at addition, must itself be a member. So I could pick any two real numbers. When I add them together, it will be a real number. And here's an example. If we were looking at integers, the set of all integers, the sum of any two integers will also be an integer. So that's called closure. Here's what it looks like in multiplication. If we have a set of all real numbers, when we multiply any of them together, we will get a number which is itself a member of the set of real numbers. That's closure. Properties of equality. We've already looked at a couple of these. We were, what did we look at? Addition. The addition property of equality, which said that if we add the same thing to both sides of the equation, it remains equal. And the multiplication property of equality said that as long as we multiply both sides by the same number, the equation stays equal. There are some new properties of equality we want to look at. You studied these back in geometry. The reflexive property. It seems so obvious, doesn't it, that A will equal A, or a thing will equal itself. It turns out that this is actually a very useful concept when you're doing proofs. Symmetric, that's saying that if A equals B, we can also say B equals A. So these two sides being equal to each other, they are symmetric to each other. Transitive. Trans says something to us, doesn't it? Something about movement. Transfer, transport. Transitive. If A equals B and B equals C, so both, you notice both A and C equal B, then it must be true that A equals C. That's the transitive property of equality. The other thing we want to pay attention to here is reasoning strategies. This is in section 11. Non-routine problems. Those are the interesting ones. Drawing a diagram. This is almost always useful. At least it is for me. I guess some of us are more visual than others, but I think drawing a diagram is quite helpful. Let's try solving this. This is considered a non-routine problem. It costs $132 to carpet a room that is 12 feet by 12 feet. All right. So this looks like a square I've drawn here. Let's say this is 12 feet by 12 feet. And we know that the cost of this is going to be $132. How much does it cost to carpet a closet that is 4 feet? Well, let's see. If that's 12, then this must be 4, and 6 must be right in here. So if we had a closet that was 4 by 6, how much would that cost? Well, one way I could look at this, let me change my colors. I could divide this thing up, couldn't I? 12 by 12 could be divided up into equal portions that are, it turns out, you couldn't always do this, but in this case, these are 4 goes evenly into 12, and so does 6. So we have in a 12 by 12 room 6, it can be divided into 6 pieces that are 4 by 6. So that means that the closet is only 1/6 of the whole room, right? That's my closet. Whoop. So, if it costs $132 for a whole room, if I divide this by 6, won't I know what it costs to do 1/6 of it? I think so. Okay, that would be, goes in twice, and yeah, so it would cost $22. So a little diagram can be very helpful, don't you think? So what did we do? Let's review this. We looked at this to understand what the problem was. We're trying to figure out how much it would cost for a smaller area. We put together a plan by drawing a diagram and then noticing that that was exactly 1/6 of the whole room. Then we put together a little expression to help us figure this out. Well, the only thing we didn't do, and it's so important, does it make sense it would cost $22 to do the closet? Yeah, it does, doesn't it? Because it's so much smaller than the room. We'd expect it to be, well, something around there, wouldn't we? Hints for your homework problems. So take this down. For problem number 2, let me see, make sure I assigned that. Oh, yes, I did. I assigned problems 2 and 3. You're going to be doing these in class, but make a note right now. This will help you out when you do it. What operation can you use to find what percent one number is of another? What operation would you use to find what percent one number is of another? Now that may not make a lot of sense at the moment. This is a hint. Once you look at this problem, it will make more sense. I just want to make sure that you write this down so you've got it tomorrow or whenever we have our next class. For problem 3, here's your hint. Draw a diagram. That's not a very surprising hint, is it? Since that's what this whole section is about. Show where the factory is and the position of each city. Then use that diagram to find the time needed to travel from each city to the factory. Now, anytime you're looking at distance and time, you're going to be considering distance equals rate times time. You've used that formula so many times in your life so far. It's just really, really useful. Remember the process. Understand what's being asked. Put together a plan to figure it out. Then do your figuring. And finally, does it make sense? One more thing to check here. This is just a look ahead. Reasoning strategies, a whole list of things you can use when you're trying to solve a problem. Because we're studying algebra, you'll find most of the time you're going to want to write an equation. In order to figure things out, you often may want to make an organized list. You're going to come across this in chapter 3. You're going to use logical reasoning. Well, when don't you use logical reasoning? Seems like you always do, but we'll look at it particularly in chapter 8. Drawing a diagram, we're looking at right now in chapter 1. Make a table, we'll play around with that a little bit in chapter 6. Simplify the problem. That seems like a really good idea. And we'll focus in on that in chapter 10. Try, test, and revise, otherwise known as guess and check. Not that popular with me, but on the other hand, that could be really useful, particularly when you're doing standardized testing. You want to be able to get to your answer quickly. Sometimes guess and check or try, test, revise is very good. Look for a pattern. Oh my. a pattern. This is actually why I love mathematics. Math is all about finding a pattern. That is, at least so far as I can tell, that's what math is about. Finding the pattern. Work backward. Oh, yes. Sometimes, if you know where you're going, it's easier to figure out the path by looking at the end point and looking backward. And of course, combining strategies. I guess we do that a lot. Combining strategies. We don't get that until chapter 14. I am very doubtful that we will get to chapter 14. We may have some eager beavers in the class who will actually get there, but I will be delighted if we get through to chapter 13. That's it for today. So you've watched 2 videos, covered 4 sections, and you've got some work to do when you get back to class.